Looking around for our amazing Rick Stump there it is. Yes, 14 is a good number. So thanks all for coming. We've got a bunch of amazing folks in the audience right now. So we have some elected officials that I want to recognize. So I'll be handing around a microphone to get some of those remarks and words. But the room is filled with a bunch of academics, researchers that work in the HAB space. We've got state and federal agencies in the room. This is one of those things that brings the people together that need to be discussing solution sets and progress in the harmful algal bloom space. And so again, just thanks everybody for joining in the room that are here, but also we have a ton of folks online and you're probably seeing that. As far as the online engagement, because we have so many people online, we're going to be fielding your questions for our speakers through the Q&A, so the chat function. So if you want to just ask a question, place it into that. I will be seeing those questions and then relaying them to our speakers, but also some of the questions we're hopeful that if the speaker doesn't know the answer to, we have folks in the room that will be able to assist with that. So again, welcome. I am going to walk around the room now and actually get a microphone to some of the representatives, the folks that are here to see these talks and talk about things that are going on in the state. So the first one I'll do is Representative Gary. So I'm going to come back here. We got a hot mic.
Feel welcomed and wanted at this point, and I'm looking forward to learning. Of course, you know, the Lake Erie is our greatest natural resource, and in the legislature, we have a lot of responsibility to work with you to make sure that we protect this great resource. So thank you for allowing us to be here today.
Yeah. Thanks, Rep. Click. Thank you very, very much. Very much. Coming to Luann, representing Rob McCauley's office.
You know, you're really anxious to see where this goes, and every year it just gets better and better and better. And the governor's been really proactive with the lake and you know, put a lot of H2 Ohio money, a lot of marshes along the lake. So that's great. Thanks.
Thank you very much, Luann. We're going to come back to Senator Gavarone as she took a sip of coffee. Sorry, bad timing.
Hi, thank you. I'm Teresa Gavarone. I'm the senator for Ohio's 2nd Senate District. So I represent all of Wood County, Ottawa County, Erie County, part of Huron County, and part of Lucas County. And I represent the largest stretch of Lake Erie shoreline than any other member of the General Assembly. So water quality is vitally important to the people in my district, but also to the people across the state. And I've worked hard in the Senate to try and show my fellow colleagues what we have going on up here at the lake. And it never fails to surprise me when I've got people coming up from other districts who've never seen Lake Erie and the awe and surprise that this is Ohio. So water quality, everyone here knows how vitally important that is in terms of recreation, tourism, drinking water, and the economy. So I'm really looking forward to the 2026 forecast, and I want to thank Chris Winslow and everyone here for all they do to protect our water.
Thank you, Senator Gavarone. We're going to come around and from Congresswoman Captor's office, we have Austin Cerna. So Austin's back here. I'll walk the wrong way.
Austin Cerno with Congresswoman Captor's office. I am based in the district out of Toledo. Ms. Captor represents the 9th district from Erie County all the way to the Indiana border. Ms. Captor is in DC this week, actually working on the energy and water bills through the Appropriations Committee. So they're dealing with the budget, GLRI, US EPA, other funding sources, and also representing the Western Lake Erie Basin, which is the largest of the Great Lakes. Ms. Captor is very concerned about the water quality issues. And Chris, thank you as always for hosting this.
Thank you. Coming to Senator Moreno's office.
Hello, everybody. My name is Roy Palmer out of the Northwest Ohio office for Senator Moreno. Senator Moreno co-chairs the Great Lakes Task Force in the Senate, so water quality is critical of importance to him. And just want to thank everybody that works in this lab and around this issue for the work that you do, and trying to continue to make this a great resource for the state of Ohio.
Great, thank you for that. And we're going to come back to Representative Bob Latta's office. David Wirt's in the room with us.
Dave Wirt from Congressman Bob Latta's district, Ohio 5. Actually, I was just on the line with the office as Chris called me. This is a very important issue, obviously, for Congressman Latta. As he noted, the House is in session this week, so he can't be here. But it's the opportunity to be the fly on the wall with the expertise in this room, the collaboration that goes on, but not just today in the room, but throughout the year. And that's why I know Chris's relationship with Congressman Latta is very firm, as well as the other folks in this room. So thanks for the opportunity to be here.
Great, thank you very much. And we don't just have presence from Ohio in the room, so I'm going to come to Senator Gary Peters. So Brian McMurrin.
Hello, everybody. Brian McMurrin with Senator Gary Peters' office up in Michigan. Appreciate everybody having us here. It's my first time to Put in Bay, and we're connected by a lot between Michigan and Ohio. Not so much football, but a lot of other things. And this is really important work that you all are doing. So I'm looking forward to learning, all the work that everyone's doing. I want to thank you too for it as well.
Thank you very much. And last but not least, Senator Slotkin's also from Michigan, Jeremy Blatt.
Hi there, everybody. Oh, sorry. My name's Jeremy Blatt. I'm Senator Alyssa Slotkin's Mid-Michigan Regional Manager. I've worked with her for the last 6 years in various roles, and I went to Xavier University in Ohio, so I do have a little bit of a connection there, but super excited to be here with you all today. Chris, thank you for bringing together this room of so many wonderful experts on such an important topic. So thank you guys for taking the time out of your days to do this and for helping share some great information across the board. So have a good one.
Great, thank you. So we're actually going to open up more opening remarks from NOAA. So as you can see on the slide that's there, so we have Dr. Steve Thur with us today. So the Assistant Administrator for NOAA, one of the chief scientists, and so the National Oceanic and Atmospheric Administration, specifically with oceanic and atmospheric research. So I'll call Steve Thur up to the microphone.
Thank you very much, Chris. I appreciate it. And I want to say thank you to the Stone Lab team that has been hosting us today. I know this is a significant lift for you all. Thank you for what you're doing. As Chris said, my name is Steve Thur. I have the privilege of working on research with NOAA. And I chose to be here today because I think this is an excellent example of federal-state academic partnership coming together to provide information that is hopefully going to solve a really pernicious societal challenge. And I wanted to be here because of the impact that the science is having on the local communities that rely upon the lake for drinking water, for recreation, for their livelihoods. It's really, really a special event. So thank you for hosting us. The overlap of interest between the agency and what is happening here is pretty tremendous. The agency sits within the Department of Commerce. And one of our goals is to promote economic development across this country. Another one of our goals is to steward the natural resources with which we've been entrusted. And it's sometimes challenging to do both simultaneously. This issue, the issue of harmful algal blooms and how it affects both the ecology of the lake and the economy of the local ecosystems, actually make it so much easier for us to fulfill both of those dual mandates with our role sitting in the Department of Commerce. And I think how we work through our partnerships is a real key to achieving that. NOAA has a diversity of activities. Most folks understand NOAA as the home of the National Weather Service, but we have a lot of other functions. And there are 4 separate components of the agency that come together to somehow contribute to the Lake Erie seasonal forecast that you're going to hear about in just a couple of minutes. Most of the work is led by the National Centers for Coastal Ocean Science out of the National Ocean Service. A huge amount of research is also contributed by the part that I lead, Oceanic and Atmospheric Research, through our Great Lakes Environmental Research Lab. But our Satellite Environmental Information Service is also contributing information that's remotely sensed, and the Weather Service has a communication set of channels that disseminate information throughout the course of the year. Maybe transparent, and I really hope that it is for those that are outside of the agency, but getting 4 different parts of one agency to work together toward a common goal isn't as easy as it should be. And I think what we've done here is an example of how we can be successful in that. If I look sort of the next layer out, our academic partnerships are absolutely key, certainly with Ohio State and the University of Michigan, but several others, and you'll hear from Heidelberg, I believe, in a couple of minutes as well. We have a lot of academic partnerships, some directly funded by NOAA, some funded by other entities that are coming together. We can't do this without partnership. And that's one of the messages I hope you take away from my opening remarks. And the last thing I wanted to say is this is the third time I've been here to Stone Lab for a seasonal HAB event. The very first time I have to reflect upon was novel. It was new. Some of what I have learned that our scientists have been developing in terms of the use of uncrewed systems, autonomous sampling, better algorithms, the advancements we have made through science in the last 14 plus years, really, really impressive. And so I wanted to conclude my remarks by saying, I hope we maintain a fertile ground for scientific creativity to bubble up, to be able to contribute new ways to advance societal challenges. With that, Chris, I appreciate the time. Thank you for hosting. I'll pass it back to you.
Thank you, Steve. Yeah, and before I introduce our next speaker, which will be Nate Manning with Heidelberg for the load information, just want to echo the remarks from Steve. This is an all hands on deck sort of thing. And so, yes, OSU and Michigan have named, but we've got Toledo and we've got Bowling Green and we've got Kent State. I mean, it is unbelievable, the academic resources that are in here. And we have representation from all of the state agencies in the room too. So this is truly all hands on deck. And I will also lift up the comment that we are making progress. We don't know everything, but we know a ton about how, if we're going to fix this issue of nutrient runoff and ultimately the growth of HABs, we know which things we get better bang for the buck than things that we might not. And so it's a good place to be. We're still not, we have not won this. We have not gotten to our 40% target, but we have learned a lot and we're doing some tremendous stuff, but it is truly all hands on deck. So as I pause there, I'm going to move to Nate. I'm coming to your slide. So folks online, this is same way it's worked in the last 14 or 15 years. We're going to do a loading presentation, and then Dr. Rick Stump will come up and give you the forecast, and then we will open up for Q&A there. Take a little pause with that Q&A, and then we'll come back and give you two presentations that are really in that harmful algal bloom space to help all of you understand some of the new science that's coming out and the great things that we've learned about. And so let me hand the microphone over to Nate. And Nate, I'm going to start your laser pointer because we want folks online to be able to see if you're highlighting anything. So that's the mouse pad.
Okay.
You can check with the back of the room on audio and the screen looks good, getting nods. Nate, the floor is yours.
Great. Thanks, Chris.
Yeah. I'm glad there's a question. That's great. But let's get to the good.
Okay.
All right.
Thanks everybody for being here. So my name's Nate Manning. I'm a research scientist at the National Center for Water Quality Research at Heidelberg University. And Heidelberg has been monitoring rivers around Lake Erie for over 50 years now. So we have a very long data set, high frequency data set. And really the goal of the Heidelberg Tributary Loading Program, which is a Ohio state sponsored Ohio Department of Agriculture sponsored program to monitor the larger tributaries of Lake Erie, as well as Grand Lake St. Mary's and the Ohio River. And really to quantify, right, the loads and the nutrients and the sediments from all of these different watersheds, right, and understand how they're moving through these tributaries into these receiving water bodies. Again, the program started in 1975, primarily with the Maumee and the Sandusky rivers. We currently monitor 16 different locations around the Lake Erie Basin, 23 in total. Like I said, we have some tributaries for Grand Lake St. Mary's, as well as the Ohio River. But today, we're focused on the Maumee, right? The Maumee provides somewhere between 5 and 10% of the water that enters Lake Erie, but about half of the phosphorus and loading that enters the lake, right? And so it's a really prime driver. Essentially, what's coming out of the Maumee determines what we see in the HABs in the western basin of Lake Erie. So how do we collect this data?
We have these sampling stations generally at the, at the downriver portion of these tributaries. We, in cases where we can, we piggyback off of the USGS gauging station, right? So where they're measuring how much water is moving through that, we're also measuring at the same place the amount of nutrients and sediment. We have refrigerated auto samplers, right? This guy right here, that's taking between 1 and 3 samples a day, depending on the river, that then gets collected, right? There's our field manager, Jake, here, collecting these tubs of sample water every week. Go out, no matter what the weather, right? Like the Postal Service, right? Rain, snow, sleet. We're out collecting that. Excuse me, collecting that data. We bring that back to our lab. We do in-house process all of our nutrients for both total particulates as well as dissolved fractions with things like colorimetry and ion chromatography. And from all of that, we get lots and lots and lots of data. Right? So we're collecting every day, we're analyzing every day, and then we can aggregate that data up into seasonal data, annual data, multi-annual, whatever you're sort of looking for, we have that covered. Now, that being said, due to circumstances sort of beyond our control, primarily some construction work that was going on in and around the Bowling Green wastewater treatment plant, we weren't able to sample in our usual manner this year. Samples were collected, however, due to some issues with sort of different protocols, a lot of the DRP data had to be filled in. Basically, there were gaps in that data this year. However, our discharge and total phosphorus data looked good, and we can use that data then to go back and estimate and fill in those holes that were in the DRP data this year. One of the nice things about having analyzed or monitored these rivers for 50 plus years is you have lots and lots of data to build models of concentration versus discharge and total phosphorus versus dissolved reactive phosphorus for these systems that we have a high degree of confidence in. So this year we did have to estimate some of the SRP, DRP data, but we feel that the estimates that these models give are pretty accurate. So what I am going to be showing you today is a couple of different fractions of phosphorus. We have total phosphorus, which is the dissolved reactive phosphorus. That's the thing that the harmful algal blooms really, really like, right? That's the Snickers bar for blue-green algae, as well as particulate phosphorus. And this is phosphorus that's bound to sediment of some sort that is being transported by the river, but often can settle out. And so what we use essentially to estimate these blooms is what's called the total bioavailable phosphorus. What amount of phosphorus is readily available to the algae, to the organisms in the lake? This is all of that DRP, right? Because it's dissolved, it's being transported by the water out into the lake, as well as about 8% of the particulate phosphorus, right? And why 8%? 8% is the fraction of sediment that doesn't settle out between where we monitor at Waterville and out into the lake. So, as the river's moving, these particles start sort of settling down as the river continues, and about 8% of that is getting out into the lake and is available. So the total bioavailable phosphorus that I'll be showing you, all of that DRP plus a fraction of the particulate phosphorus. So can't talk about loading without talking about water. Discharge at Waterville on the Maumee River. This is March 1st through June 16th, so last week. What we see is that the highest discharge events occurred really here in April, right? One big event really in April. And then through April and into May, we had essentially a higher baseline of discharge than we would normally expect, but no big peaks like we saw with that early April storm. Right. Overlaying 2005 here in the sort of purpley, you can see again that early April peak that we saw this year. We also had last year, but there was a secondary peak in 2025 in sort of early to mid-May that we did not have this year. And 2024, again, here in green, you see this early season, early April storm event that really, sort of head and shoulders above any other storm event that we have during the spring. And again, April or 2024 had a secondary storm that we don't see in 2025 or 2026. So the timing of the major storm event from 24, 25, 26 this year all line up really well. 24 and 25 had secondary high storm event discharge events post that big storm, whereas in 2026, we didn't have that big secondary peak, but what we did have was sort of elevated river levels, elevated discharge levels, sort of dragging out across the rest of April and into May. So total bioavailable phosphorus loads, right? Concentration, how concentrated the water is, or the phosphorus is in the water, times how much water there is, gives you the load, the total mass of this nutrient. And we can see here, these orange dots, these are the daily load values for total bioavailable phosphorus. And we can see they match up, right? They follow along with how much water is moving through that system really well. Right? And this is one of the ways, again, that we can go in and try and fill some of that data in, because we know sort of where that data should be based on how much water is moving through the system. Okay. And then cumulative load. How much of the total amount is being delivered from one day to the next? The sum of each day from March through July. And this is this purple line here. And you can see when we get to that big storm event in April, it shoots way up, right? And then sort of climbs a little bit as we have these sort of higher baseline flows and then levels out as we get into May and early June. About 75% of the total load from this spring was delivered in April, and 60% of it was from this one storm event, right? So a lot of what we're seeing this year in the loading this year is really being driven by that one big storm event in early April. So where does this sort of line up? Putting this together, sort of the last days that we had solid data for, the 16th, June 16th, we were at about 293 metric tons. The target is 240, so we are over target, but not by a huge amount. And the projected out to the end of July, right? So looking ahead 5-6 weeks, we should be at about 304-ish metric tons, based on the projected data from the National Weather Service. So not a lot more loading is expected, through the end of June and into July. We've sort of gotten the majority of what we're going to get, and it all came in April. So how does this year line up with other years that we've looked at? So the maximum loading that we've seen over the years that we've been looking was 2015, right? The big bloom in 2015 was driven by the most loading that we've seen. Minimum 2012, right? There was a really mild bloom year. But we can see that 2022, 2023, 2024, 2025, 2026 are all clustering together, right? And so the last several years have been very similar to each other, and 2026 looks a lot like 2024 in sort of where it's going to end up, right? If you follow these lines, there might be too many of them that might be a little hard, but this blue line is 2026, right? And we see the big April storm, everything came in that storm and then it levels out. Where 2024 sort of followed a slightly different path, right? Had a couple of big storm events, but we get to about the same place in that 300-ish metric tons. So 2026 and 2024 look really, really similar. So how does 2026 compare to the past loads that we've seen? Looking back in time, back to 1982, each one of these bars, these blue bars, is a 5-year average, and each one of these dots is an observation a year within that 5-year average, right? And so we can look and see, does this year sort of line up with the 5-year average? Is it higher? Is it lower than sort of what we would expect looking back in time? And what we see, stream flow, how much water is moving through the system. We're right about where we would expect for that 5-year average, right? The star here, as of June 16th, we were at about 627 billion gallons of water that came out of the Maumee. The long-term averages are, closer to 800 to 900 billion gallons. So we are down when we look at long term. But if we only look at the last 5 years or so, sort of years that look very similar climactically to this year, we're sort of right where we would expect it to be. Total particulate phosphorus. Again, this is the phosphorus bound to sediment. We're actually a bit higher than we would sort of expect. It's not the highest that we've seen in the past 5 years, but it's high. Whereas dissolved reactive phosphorus, right, the one that makes up the majority of the bioavailable phosphorus, again, comes in right about sort of where we would expect based on the last 5 years or so, right in the middle, basically, of where we would expect DRP loading to be, right? So we're at about 200-ish metric tons. Expected would be about 203 metric tons. So we're close on those, right? For concentrations, right, loads are defined by concentration times discharge. When we look at the concentrations, essentially how much is in each sort of unit of water. Again, total particulate phosphorus, we're higher than we would like to see it. Not the highest we've seen in the last 5 years, but higher than sort of the average, about 0.465 milligrams per liter of particulates, whereas DRP, again, pretty similar to the 5-year average, about where we would expect based on the last 5 years, 0.08 milligrams per liter. The average is 0.078. So we're sort of right in the middle of the last 5 years this year. So again, are these where we would expect them to be? We can look at the load versus the discharge. And if we see, 2011, 2015, the two biggest blooms, we're up here on the upper right-hand corner of these graphs. 2012 to 2005, some of the smaller blooms are down on the lower left-hand. And if you're right on this line, right, this black line, then you're right where we would expect the loading to be based on the amount of water that's coming out of these systems, right? And so I'll show you the total particulates, the dissolved reactive, and the total bioavailable phosphorus, the one that is important for the bloom. And again, remember that TBP is all of our DRP plus a little bit of the TPP. So for total particulates, again, this year we're high. Lots more particulates, mostly driven again by that April storm. Dissolved reactive phosphorus, basically bang on that line, right? We're right sort of where we would expect to be based on the amount of water that's coming out. And because of that, our total bioavailable phosphorus, a little higher than we would expect based on the amount of water, but again, being driven by that large particulate load that came early in the season. So in conclusion, April storms, really one big storm in April was the primary driver of loading for 2026. Up to 60% of the total load was delivered in that one major storm event. The projections out to the end of July indicate relatively low contributions for July. We expect it to be relatively flat from here on out. Overall, this year looks remarkably similar to 2024 in sort of endpoints, right? How they got there, right? The path they got to that endpoint is slightly different, but where they end up is very similar. Total particulate phosphorus load is higher than we would expect. We're getting more sediment than we'd sort of expect based on the amount of water. Whereas DRP load, right, the one that we're generally focused on, is right about where we would expect it to be. So total bioavailable phosphorus, the stuff that is driving the blooms, is really being sort of driven, being influenced mostly by high particulate loading, particularly early in the spring, right? March and April. These are periods of time when, fields haven't been planted yet. There's not a lot of activity yet on those fields. And we may be getting increased bank erosion from these high intensity, right? Saw how large that storm was in April. A lot of energy moving through that system. We may be picking up an awful lot of sediment from the stream banks from that. So one other thing that I'd like to bring up, all the data that we collect is public data and should be available to the public. And to that end, Ohio Sea Grant and the Ohio Department of Higher Education, HABRI, sponsored a project for Heidelberg, and my postdoc Colleen is here. She developed this new dashboard for all of our data, and you're allowed. It's open to the public. We encourage everybody to go and check out this new dashboard. You can look at all of our rivers over time. You can produce lots of different graphs, right? Visualizations of the data. And one of the prime drivers here was, to make this public data public, right? And make it accessible to the public in a way that is intuitive for, lots of different sort of experience levels, right? So you can see overviews of our rivers, explore and download our data. And in the future, we're not there yet just because of issues with, federal data versus our data. We will have the USGS data for the Maumee represented on this data set as well. We just have to get, through some hoops on the federal level to get that data presented on a non-USGS website, basically. So the data is out there. Our data portal is now live to the public. So please go and check that out. Thank you.
Thank you, Nate. All right. While I pull up the next PowerPoint presentation, we will do questions after Rick. So we'll have questions both for Nate and Rick after the second presentation is done. But again, thank you, Nate. That was perfect. I'll pull up your PowerPoint, Rick. So Dr. Rick Stump with NOAA's NCOSS, so National Center for Coastal Ocean Sciences. I always screw that up, but I think I got it this time. So we'll go to presentation mode again. Rick, we're going to ask you to use the PowerPoint laser over here so the audience can see anything that you might need to highlight for them. So sir, the floor is yours. Here's a microphone, forward key, and your laser pointer, sir.
Okay. Thank you a bunch, Chris. Thank you so much to Stone Lab and Ohio Sea Grant for having us up again this is the 14th time. It's this extraordinary facility, and it's great to not only talk about it here, but for all people coming here to see what is going on in the whole region. So for our forecast, we do this work with a collaboration which runs across NOAA. We very involved with the Weather Service. The Heidelberg data is critical to this because the nutrient loads are essential to driving the blooms. And the models we work with also, we get outputs from models from the University of Michigan and North Carolina State University. So really appreciate their assistance as well on it. So I'll go on here. Let's see, arrows. Oh, there. Hey, little backdrop here. We've got analysis of data, a view from satellite for 26 years. And you can see how the blooms, they've shared between years. This is the peak each year. And first noticeable one was 2003, and then there was a series from 2008 up through 2011. It continued, 2008 to 2011, and then some other ones afterwards. What I'd want to note is the blooms vary a lot between years, and these peaks kind of capture that. And if you look at when I show the three largest blooms, 2011, at one point, this was in October, it was way past Cleveland, as well as the Canadian shoreline. So very dramatic difference overall. The 2015 bloom, which was almost as much in biomass, total quantity of algae in the water, you can see it didn't cover the same, but it was very much into the Central Basin as well. And then 2017, a bit smaller, but phenomenally intense. Those in Toledo might recall there was scum from the Maumee River in Toledo, but it went all the way across the lake to Leamington, Ontario, scummed the whole distance. Very intense. It looks small in area, but phenomenally intense by all that red color. So these blooms change a lot. You can see it can show up at the peak in different parts of the Ohio coast, Ontario coast, Michigan coast as well. I'll touch on this theme more than once here. Last year, for a recap, it was a mild bloom. Forecast severity was between the 23 and 24 bloom. The severity index, a 10 is the worst bloom we've seen, which is 2011. Presumably, we'll never exceed a 10 ever. It is possible the way the index is defined, but there's progress being made, so we shouldn't go there. So the scale last year was a 2.4, and you can see the difference between the 2024 bloom. This was a bit less severe, less areas of red, those bright red areas in the 2024. At that particular week or two, there would have been a lot of scum in that region, a lot less scum as well. And you can notice the positions, they happen to be a little different as well. Little recap on the phosphorus loads, because phosphorus is critical to driving the bloom. And 2026 is quite similar to 2024 as far as the total load, and a bit more than 2025. And of course, the others, for reference, the highest load observed was 2015. And a comment for many of you, Nate talked a lot about an April one, and there's probably a lot of people from the rest of Ohio, and it rained a lot. And you might wonder, well, what happened? And if you notice the circle there, that's the rest of Ohio, and there was up to 10, 12 inches of rain in areas, huge floods. And that's where the Maumee River is. So we missed, this area missed something that would have been historically bad. We were very fortunate by that. So this is very typical rain for the month, inch, maybe even slightly low, inch or two of rain, very typical. So for those who wonder, yes, we really did dodge something up here in May. The outlook for the rest of summer, weather, the temperatures, kind of typical. So the variation, expect perhaps a little more precipitation than usual. Our forecast kind of that's built into our forecast in a couple of ways, both in the models and also in some adjustment, but it might be slightly wetter. We're not talking really wet. We're not talking floods. Just it could be, it's at least going to be normal rainfall to a little wetter than usual. Part of the reason for that, by the way, is all that rain that fell in southern Ohio left a lot of water there. And so as that evaporates, you all know about corn and all, well, a lot of stuff evaporates out. If we get a southerly flow, some of that could show up here and cause a little extra rain. Not huge rains, just potentially more. So that's a consideration. You're probably hearing a lot about an El Nino and with questions about what that might do. This is the El Nino forecast, and there is an El Nino going on now. These colors here, if it's pale, it indicates the presence of the El Nino. The dark red indicates it being worse, and this is forecast from now into next spring. Right now, we're at mild El Nino overall. And this is a tropical phenomena that, because global weather, there's a term called teleconnection in the weather. So weather patterns from the tropics spread out to other areas. There's influences up here, but it's not as direct as in the tropical regions. or in the very southern US. They get a very different response. But you can see it will be increasing, but it's going to be the severe that you're hearing about is late summer into September. That's September, October, in the fall, and the winter. So any effect on this area will be in fall, winter. It's much too early. So we're not going to expect that here as an influence. It's for the forecast. So we have a model. We include we both use the bioavailable phosphorus in some form, and loads from March to July statistical model, and the University of Michigan, North Carolina State uses a Bayesian model, which I'm sure we can happily talk about if you want to, but I'm not going into modeling details. Both groups are experimenting with some new models. We're looking at those, but they're not yet incorporated in the ensemble. They are behaving somewhat consistently. Total load right now is about 296 metric tons as of just this past week. Whoops. And so from this, what we're forecasting is a bloom of 3.5 with a potential between 3 and 4.5 for the severity. This puts it in the moderate bloom range. This is due to the slightly above normal spring. This does account for the normal July rainfall and some accounting for a little bit extra elevation on the rainfall. If we do get that extra rain, then we could be more up at that 4.5 range, but we're in the moderate level. This puts us a little more extreme than 2025 and less than 2024, but we're looking at probably something similar to these two blooms, 2022 and 24. And I show these up particularly because you'll notice at their peaks. This is the peak, mind you, not the whole. The blooms grow and then they show up and then they go away. 2022 peak was kind of mashed up against the border, Michigan, close to Michigan and that side. Whereas in 2024, along Ohio and further out into the basin. And these changes, this is shifts in the wind pattern. So if we have a steady northerly wind of sort, Ohio's going to have it. We get a shift to southerlies, it'll move out into the lake, or a little southeast, it'll end out on the Michigan shoreline. This varies. We're trying to work out if we can have any skill at forecasting, if it's likely to go one way or another. There are models that go out that far where we've shown some promise with this, but we'll see how this goes, because everyone would appreciate, we have people from Michigan, you would really like to know how likely you're going to get it. And of course, everyone in Ohio, how likely. And the Ontario people are always happy when the wind's out of the north, so they don't have to worry about it. We produced daily satellite imagery. This was June 20th. Yesterday was actually a gorgeous image. I didn't pull that up overnight. Where it's pretty calm. There is a little bit of a bloom in Sandusky. I actually confirmed that yesterday. There's a water sample in the back if people want to see what Planktothryx looks like. That's well in the bay. But the rest is calm. There is a spring bloom going on. In fact, I will note, I think, we have the laser. This little bit of greenish water here is a spring bloom, typical diatoms and such. That's actually still going on in the area. There's actually diatoms out here in Put-in Bay as well. This gets generated daily, and I'll touch on that. Temperatures this year are running right about normal. Last year was quite warm, and you can see the 2024 red line right in here. Whoa. We're right here. In 2024 ran quite warm. This temperature does not affect magnitude. It's very important to understand. You need nutrients to produce the bloom. Temperature helps it grow, but it just might grow faster, but it will ultimately peak when it runs out of nutrients. Last year, the bloom started early July. 2024 started early July. Last year, it was actually a bit later, mid-July. So if we stay in this cooler side, well, we're expecting somewhere, it's been cool so far, so it may not start up at that early time. And this is just right now, the temperatures are 5 to 6 degrees cooler than 2024. So hopefully we won't see any first sign of it until later on. I'll also add in, we're now adding in a new data product, high resolution. This is every 5 days from Maumee Bay area. It's only chlorophyll. It does not tell us what the chlorophyll is, unlike our standard product, which is specifically for the bloom, but at least indicates the presence of it, very high resolution. So it may be of some use for like Maumee Bay State Park or some of the other areas. If you're wondering, when the bloom finally really goes full strength, the chlorophyll is cyanobacteria. So it may have some value. We're experimenting with that from our page. All of those you can get to from our forecast page, the QR code at the bottom. The link is also up here as well. The forecast, you can download a PDF of the day's forecast, what we have, the image products, and any text we produce. We have a summary of current conditions, and the outputs are the location of the position, the forecast position, and any mixing. The mixing part would be, if you're a boater, you might want to know, is there going to be scum tomorrow or non-scum? The mixing forecast will tell you that. If it's someone who's a water intake manager, would want to know if it's mixed down into the water closer to their intakes. So we have that forecast. You can subscribe to that at the bottom, and we have additional links on our page, both to our HAB monitoring page and also to other things, other sites, information from Ohio EPA as well. Very important if you're interested in the water sample data from our Great Lakes lab, you can get to that. Can't say enough for their support. Reagan Herrera in the front row here, you wave your hand, right? She runs the program. We have a few other people from Blairell collecting toxin data, particularly. With satellite, we can only see how much bloom there is. We can't tell you how toxic it is. And so that's really important information to get. That's done weekly. So additional valuable data. To sum up the forecast, we're forecasting a moderate bloom, 3.5. The likely start in July. It'll start appearing. Again, it will not be full force. It'll start and grow. We're exactly when, we can't say, but it's been running at least in the first few weeks of July, some evidence. Intensification in August in the Western Basin, and this should be pretty much mostly confined to the Western Basin. We shouldn't see it past these islands. Continuing to September, the duration very much depends on the weather fronts as well. That is quite variable. That's probably the biggest factor. Those fronts, the winds disrupt the bloom, and the changes in temperature at the same time cause it to stop growing, and so you have a mortality and you lose the bloom. That's really variable between years. In the last few years, it has been ending in September. Location changes with wind direction. The highest concentration areas, like as we report in satellite, those are most likely to have scum during long wind, low wind days. And I can't emphasize enough, the scum has phenomenally high toxin levels. It can be concentrated 100 to 1,000-fold. So keep your kids, your pets, your dogs out of scum, please. If people think their dogs are indestructible, they do die from this. Can't emphasize enough. We have the website for plume location, scum forecast, and so enjoy the lake. The bloom is not everywhere. It's not all the time. There's plenty of great places to go swimming and boating in Lake Erie. Thank you.
Check the audio back there. Are you hearing me? Thumbs up as I walk around. Good. All right. So we have both Nate and Rick up here at the front. I will already apologize in advance. We've already got 50 some questions coming in. The way we want to do this is we've got a lot of press in the room and online. So we're going to field those questions first, and then we'll get through as many as we can. So I'm going to read from online. If there is a question in the audience, do feel free to raise your hand. But again, I'm going to be juggling the questions at the front of the room. And also, these are two brilliant men. And I'll try and help out where I can. I wouldn't categorize that as brilliant, but there are a lot of amazing academics and agencies in the room. So if a question comes in and you want to contribute, that's why you're here in the room, is to weigh in on these things. You guys are clearly the experts in this topic. And so again, I'm going to try and hit the media questions first. Some of these may have already been hit. I tried to eliminate some of those that were really hit squarely, but there are some in here that I think we need to revisit a little bit. Let's see. So, one is as global temperatures rise, and I believe you hit on this a little bit, and winters in the Great Lakes get shorter. What is the potential for these harmful algal blooms to grow and reach places like Dunkirk or Buffalo? So I think it's really more in that idea of like, can you give us more insight on maybe more mild winter, warmer temperatures? What do you think that that might do for future forecasts? Anyone in the room? Or
I'll start off with that. Kind of recapping the point on temperature is the bloom size is determined by the nutrients. And so temperatures will say how fast they grow, but unless the temperature can somehow alter the nutrients, which is not, there's not a mechanism for that, that's not a concern. So the likelihood of these blooms going to Buffalo, no, you'd have to have a bloom far larger than anything we've ever seen to get that.
Yeah, along those lines, one thing that I would bring up, Lake Erie is really sort of like three different lakes, right? All stuck together. The Western Basin, the Central Basin, the Eastern Basin. And, you know, chemically and physically, they're very, very different from each other. The conditions in the Western Basin are like absolutely perfect for these harmful algal blooms, right? It's shallow, it's warm, has lots of nutrients. And as you move east, it gets deeper, it gets colder, you know, there's less and less nutrients available. And so, you know, just the physical characteristics of the lake sort of isolate it to this western end of the basin, or the western end of the lake.
looking to the room to see if there's any additions. So, Tom, question. Tom Henry from the Toledo Blade, please.
Couple things, Rick, the range of 3 to 4.5, correct me if I'm wrong, but that's a little narrower than what you've done in the past, like 1.5. I'm just wondering if that's a reflection of your confidence in the forecasting, and also just your visual observations on the way over. Since we're only days away from July, you know, we may not have gone through any thick scum on the way here, but it's not crystal clear blue either. I'm just wondering if you have any thoughts of, I'm not asking you to predict which day in July, but is there any just visually any belief that the bloom may be starting now?
There's right now, there's some dissolved microcystin present in the lake. Blair Reagan right behind you has observed that. We don't have particulate microcystin now, which would definitely indicate active start. We've seen some cyanobacteria in Sandusky Bay that I mentioned. But out here, no. I will say the bloom will start on a Thursday. I just won't tell you which one. As far as the range on this, the low end is reasonably defined based on the load we have. The reason it's a little narrower, like the last 2 years, there's been a lot more uncertainty in what was going to happen in July. So even while I'm saying we've got some uncertainty about more rain, there were weather patterns setting up in the past couple of years where there could be flows coming through from Iowa, coming right through here. And you've probably heard they grow a lot of corn in Iowa, and corn evaporates a lot of water, and all that water goes in the atmosphere. And so you get any disturbance, it can come here. And that was a problem we were having the last couple of years, where we had the right conditions that anything happened and it would rain. So we've narrowed this down because the weather patterns we're expecting to see look a little better. A bit of a northwest flow, which is more favorable for a little lower risk overall. So that's the reason we've reduced that.
That's just planktothrix in Sandusky Bay.
There's planktothrix and it's a mixture of things. Some Phanozomenon, I think Justin identified as well. And it's pretty localized right now.
What does it mean to return planktothrix? There had been a few years where
it's a mix of stuff right now, and this is local. I just heard from George Bollerjohn's group that given that turbidity in that western, I was over by Pickerel Marsh, and that's where we're seeing in that far southwestern, very turbid, little different environment than the rest of the bay. So it's not surprising we get that. Right now, I don't think it's not big enough to say that we really have a return to the massive Planktothrix blooms that Sandusky's had in the past. Although last year there was a bad, but it wasn't Planktothrix. It was a really bad bloom of Ephenazomenon and other stuff, scum formers, which was not good. At least Planktothrix doesn't form scum. So we'll see how this shakes out. But it's premature to say that Sandusky's returned to a Planktothrix environment.
Thanks, Tom, for those questions. And I just want to highlight the one about temperature and precipitation patterns came from Dave Freeman and Mackenzie Showman online. So you have the reports. But one of your responses, you called out Dr. Justin Chaffin, OSU, George Boylston, Bowling Green State University, Mike McKay, that's at University of Windsor. This, again, is an all hands on deck kind of thing. So I just love that. Nate, you may be able to address this, but I know other people in the rooms too. We got a question from Tom Jackson saying, I'm hoping there will be a discussion on whether wetland restoration appears to be helpful. So I don't know if, Nate, you want to take a crack at that one, and then I know we've got some other folks in the room here.
Yeah, so the H2 Ohio program, the Wetland Monitoring Project, has been looking into that, and has yielded some results for phosphorus and nitrogen. I think it's still premature to say how much of an effect these wetlands are having, but they are effective. Right. And some are more effective than others. Right. I think as we are looking at these wetlands, one of the things that's jumping out is how you design these wetlands really matters. Right. Depending on what you want to do with it. Right. Are you interested in phosphorus? There are designs that work really well for phosphorus removal. There are other designs that work better for nitrogen or sediment. And so do the wetlands help? Yes. Yes, yes, yes. Yes, and yes, and yes, they do. We're still trying to figure out sort of, how much of an effect the ones that have been built in Ohio are having versus sort of what those designs are best at.
Yeah. Good, and I'll come back. I know, so under the governor's H2 Ohio program, and thanks to the legislature for supporting that, we have done some wetland placement. I've got a lavalier, but you could move. And so there's been some of that investment through H2 Ohio to construct wetlands, but what I will do is also applaud the DNR, specifically Director Mary Mertz, has actually put a monitoring program in place to then not only construct, but let's see what that does. And so I know we got two DNR folks in the room right now with Eric Sauce and Janice Kearns. Bringing you a microphone, anything else you'd like to add, point to each other, who's on the hot spot, hot seat, but I'd love some remarks if I could from the DNR. And I will add, while I'm walking back here, the DNR was able to do this wetland monitoring because they recruited a group called LEARN, so the Lake Erie and Aquatic Research Network. And basically, it's 6 universities, 30+ students, grad students, staff to monitor these wetlands. It's been, again, all hands on deck. Eric, please.
Yeah, and starting in as Eric Sauce, H2 Ohio Wetlands Program Manager for the Ohio Department of Natural Resources. Beginning in 2019 with H2 Ohio, the DeWine administration recognized that we needed to go all in on what we can do in the landscape to keep the lake a beautiful place, a nice resource for Ohio. So we have done a historic amount of wetland restoration through the H2 Ohio Wetlands Program. And we knew doing that we would also need to track the progress of what we're doing and learn from it. And we really have. And I would point to the new 2025 Wetland Monitoring Program's annual report that'll be coming out very shortly with a lot of good news, frankly, about what we're doing. So stay tuned on that. Do we know approximately when to look for that? In August. So that would have the new 2025 report, which has very good indications of what's going on in the Maumee and Western Lake Erie Basin. Thank you.
I have last year's report on my nightstand. It is an amazing read, so please make sure you download the new version. Okay, there are a lot of questions in here that came from the media and other folks in the room, but I think after the next 2 talks, might answer some of those questions. So rather than ask them now, so folks that have submitted online, I'm not ignoring you, but we'll get to some of these other questions. But I will also, the one that came up, again, not from the media on this one, but Nate, is nitrogen also being monitored? I thought HABs was mostly dependent on nitrogen. So can you take that nitrogen question out?
Sure. So yes, nitrogen is also being monitored. We at Heidelberg look at nitrate, nitrite, total Kildall nitrogen. So we're looking at, organic and inorganic forms of nitrogen. They tend not, the nitrogen is what's making the blooms toxic, right? The phosphorus makes them big, the nitrogen makes them toxic. And so when we're talking about the bloom extent, right, the size of the bloom, we're really interested in phosphorus and how it drives the growth of these cells. When we talk about the toxicity of these blooms, then we're interested more, looking at the nitrogen, how much nitrogen is available to these cells, to these different different organisms, because those toxin molecules are super heavy nitrogen. They have lots and lots of nitrogen in them, so they need lots and lots of nitrogen to build them. And so, is nitrogen important? Yes, absolutely, it's important, and it can help with growth as well, right? Nitrogen is important for all sorts of different functions, but phosphorus is what's driving the size of the bloom. Nitrogen is what's driving the toxicity.
Great. And just to add on to that, Nate, because I think there's kind of a misunderstanding, because we talk about both those things being critically important. People are saying, then why don't we talk about the nitrogen? And so really for us, we know, and from a lot of the studies, I know Dr. Justin Chaffin works on it here, if we can tackle that phosphorus, even if nitrogen is there, the bloom isn't there to be toxic. So it doesn't say, because they're both equally important, that we should switch gears and not target phosphorus, right? And so that just...
Right, absolutely. And our ability to sort of forecast the toxicity based on that nitrogen is improving. And Dr. Sylvia Newell's here, and she has a grad student who has a model of forecasting that toxicity that's being worked on.
Please, if you can. So Sylvia Newell, director of Michigan Sea Grant.
Hi, everyone. Yeah, I would just add one thing to that, which is to say that there have been some modeling studies that have come out that have suggested, others don't agree with it. Some have suggested that we could, if we controlled phosphorus but had very high nitrogen, end up with small but highly toxic blooms. It would depend a lot on the species, I think, that showed up. And there are non-toxic strains of microcystin as well, but basically when there's a lot of extra nitrogen around at the beginning of the bloom, that's when they start building that particulate microcystin inside cells. And so if there's not a lot of extra nitrogen around, then they don't build it. So that's what we're hoping for in the future. And yeah, we'll see how well the forecasting toxicity works. If it does, we're sending the code to Rick, and if it works, you'll see it next year. If it doesn't, give us a few years.
Thank you, Sylvia.
I'll just one comment on the phosphorus, that if the phosphorus concentrations get down enough, we could switch to a different environment. So we could not simply have cyanobacteria blooms, in which case we're in a new ecosystem, a complete state change, if we can get the phosphorus down enough. That is a possibility.
I see Tom's hand went up, but I'm going to limit you to one question, not a series of 3 back to back, Tom. We got to get to the next one.
All right. Well, then I have to choose between a couple different ones here.
Rolodex of questions.
Yeah.
Please, Tom.
Rick, maybe could you elaborate a little more on the near miss we had, the historic rain or potential historic event that came to central and southern Ohio, but not northwest? What it could have meant if it had been uniformly spread across Ohio and hit our region too?
My response to that is I do blooms, I don't do weather. It would have been that whole April flow. We would have seen another one of those April events at least. So you picture that thing on the graph, add another one on top of it. That would be the minimum that I would say.
Yeah, you would be looking at, discharge and loading similar to 2019. maybe not as high as 2015, but getting close. So we did, in that sense, dodge a bullet a bit. That we did not have sort of that second huge peak that Southern Ohio did get when you look at their discharge numbers.
I'll just build on that. The fourth speaker, that speaker will talk to you about how much discharge ties to the bloom. So anytime you're going to get a storm that you didn't have before, it will have an impact. That's Cal Buelo. He's coming up in a little bit.
Yeah.
I do want to get to the next speaker. I see your hand, and we'll come back to that one after we get in. So thanks, you two.
Yeah.
Give Grace one of the microphones. The other one can sit on the camera. So titles here for you. So we're going to look at aerosolization and transport of the toxins in the water and how that might impact human health. So please welcome Grace Young. She's a PhD candidate. Yes, at University of Michigan, we hate each other on the court and the field, but academically, research-wise, we're buddies. We go way back. We're buddies. So Grace, the floor is yours. Forward arrows, and you can use the laser pointer with the mouse pad. Please.
Well, hello. Like you said, I'm Grace. I'm from the University of Michigan. I'm a PhD candidate in Andrew Alt's lab. And today we've been hearing all about the forecast. And what I kind of want to talk about is how the blooms don't just exist in isolation. There's air above these blooms. And what I want to understand is how the bloom interacts with the air to know that is there any impact of these blooms beyond just what they are in the water. And so the word aerosol can mean a lot of different things to different people. So before I get going, I really just want to say what it means for me. And so when I'm talking about an aerosol, what I'm talking about is a bunch of particles that are floating up in the atmosphere. And if we all just take a deep breath in together, how many particles do you think that you just breathed into your lungs? You don't actually have to answer, but it would be on the order of around 500,000 to 1 million particles for every deep breath. And that's because each little bit of air has around 5,000 to 10,000 particles floating around. And when we're talking about these particles, they're classified and regulated based by their size. And two of the ones that are regulated are coarse and fine particles. And I just kind of want to give you, put into perspective what those sizes look like. So if we have a sheet of paper, it has a thickness of around 1,000 microns. And in this thickness, you can fit 10 coarse particles. And then in one coarse particle, you can fit 4 fine particles. Sorry. Where's it going? And we care about these sizes because these are what's regulated. They're regulated based on their size because the smaller the particle, the longer they can last up in the atmosphere. If you have a really big particle, it's just going to splat right back down on the ground. If you have a 1 micron particle, it can last up in the atmosphere for around 12 hours. And if it's lasting that long up in the atmosphere, they can be transported. And so here I'm just kind of showing you some global aerosol movement. And so these particles don't care about city or state borders. It doesn't care if it's Michigan or Ohio. They can transport. So if it's in Toledo, it can make its way to Cleveland or Detroit. And that's important for us to know. And there's a few good examples on this video. But if you see the blue, this is sea spray, and this is coming from oceans. You can see it transports all across the world. But what I think is even a better example is the purple. The purple is dust from the Sahara. And if this video went longer, you would watch it go across the ocean and it'd get its way to North America. So it can transport very far. And if these aerosols are being transported, we need to know what their impacts are. And they have health impacts. And this is because coarse and fine particles are regulated for their size because they can get up in the atmosphere and last, but the size is also determining where they can deposit into the human body. So if you breathe these particles in, the coarse and fine particles are small enough where they can get into your lungs, with the fine particles being smaller where they can get very deep into that intricate part of your lungs. And there's health effects with that. Both coarse and fine particles are linked with cardiovascular and respiratory diseases. And our largest source of aerosols in the atmosphere comes from bubbles in oceans and bodies of water. And so if anyone's walked across a beach on specifically the oceans, you've probably smelled sea salt. You were actually breathing in these particles that are coming out of the ocean. But for us, we live near the Great Lakes. And I think it's funny in the summer, I always see people with no salt, no sharks, no problems, or no worries of that sort. I see those everywhere. So it's very obvious to us that we have different water. But when we're walking across our beaches, we're not actually able to smell anything. But that doesn't mean nothing's getting aerosolized. And so when I'm talking about particles, specifically when I say lake spray aerosols, I'm talking about the particles that are coming out of the lake, specifically freshwater. And the way these are formed is you have a wave breaking, and you can get wave breaking in these lakes. And so the photo that I first showed was a wave from Lake Erie, and they can be formed. And so when you have your wave break, you have bubble formation, and that's just air getting stuck in the water. And I did love seeing the bubbles on the board because it is my research. And when you have this bubble formation, then these bubbles can merge to form larger bubbles. And if these bubbles are in the water, anything in this water can adhere to that surface. So something from a harmful algal bloom, if it's dissolved, it can adhere to the bubble surface. It doesn't necessarily have to be from a harmful algal bloom. It can just be literally anything in the water. If it wants to adhere, it can adhere. And when it does adhere, when this bubble bursts, it becomes aerosolized. And so we know that harmful algal blooms have gone through this process to be aerosolized. And we also know that these particles can be transported a couple miles inland. And so really what we want to understand is this an important source of aerosols? Because it really hasn't been explored all too much. And that's really what we're looking at. And so the first place that lake spray aerosols were observed was in 2010. And what you're looking at here is your particle number. So how many particles got out of the water versus their sizes. And like their size is important for their health impacts. So these are small particles, these are large particles. And when they were on land testing or doing measurements comparatively to the lakes, they saw a substantial increase of small particles when they were near or by a lake source, meaning this isn't a very important source of aerosols specifically for us locally, where we need to understand what's going on. And so that's why we're interested in having a deeper understanding of the aerosolization process to improve modeling and inform our health decisions. And so the way this works, what we're doing is we're doing season-long field sampling. So we don't just want to sample when the bloom is at its peak. We want to know how the aerosols are changing throughout the whole season. And so what happens is we're using these instruments here, and you can kind of think of them as some glorified vacuum cleaners. They just pull in aerosols, and we're able to look at them later. But the challenge is, if I'm out in the water, how do I know what's coming from just the water? And so that's why my lab takes a two-prong approach. So we take water back from the lakes and we put it into this box. And this box has been checked multiple times to make sure that it's making particles that are representative of the fresh water. And in this, we can look at specifically what is coming out of the lakes without anything interfering with it so that we can understand the impact of just these aerosols. And by putting these two pieces together, that's really why my lab is one of the leading people in really understanding this aerosolization process. And just to give you a few examples, there was a study done that we went to Lake Michigan and we collected particles, and where we are actually able to see what a lake spray aerosol particle looks like. So it's this little block, it's around 300 nanometers, very small. But just by looking at this, you wouldn't know what it is. So we had some very fancy tools, and we were able to get this chemical information. And so each of these spikes or each peak is giving us information from the calcium and then the carbon and oxygen peaks. We know that it's a lake spray aerosol, as well as it was very close to Lake Michigan. But we want to look at Lake Erie. So I had the opportunity last summer to go out onto a boat with some collaborators who are here in the room, and we had so much fun. And I'm actually holding one of those glorified vacuum cleaners. But we were able to collect particles, and this is where I was able to kind of figure out how do I want to go about my sampling during the whole bloom this year. And so this was really used as kind of like a test run, if you want to think about it. But in this, I was able to get basically a particle fraction type. So meaning out of 100% of the particles I looked at, how many were biological and so on and so forth. And it was really exciting to see that I could tell the sediment apart from what was biological in the lake. But also, this is exactly what the models need so that we can further improve them, because we need to know the aerosol composition of what is getting out of the lake. We also know that these particles are able to incorporate into the clouds. So this study took a plane and sampled through a cloud and above a cloud. And in both of them, they saw a contribution from these lake spray aerosols, meaning if they're incorporating into the clouds, it can influence cloud formation and cloud properties, but they're also getting above the clouds, so it can be transported farther inland since they're able to get so high. But we're here to talk about harmful algal bloom. So really, how does this all tie back into it? And so for a while, people kind of assumed if you knew what was in the water, you knew it was in the air. But in this study, they were at Mona Lake, which is in Michigan, and they looked at different concentrations of chemicals that were in the water. And the types of chemicals we don't really need to get into, but I'm just going to point out the purple, the gray, and the red. And if you just look at those, these concentrations are in the water, you have the highest concentration in your purple chemical. And when you compare that to what's in the aerosols, it is not the same. You get almost none of the purple chemical, mostly the gray, and then a little bit more of the red. Meaning that some things want to adhere to that bubble surface and some things don't. They're just like chilling in the water. So we really need to understand what's getting aerosolized, because we can't always make the assumption that if you know it's in the water, you know it's in the air. And so I actually love how planktothrix was talked about, because I'm going to talk about it in a second. But by looking at these particles, we use a very special tool called OPTIR. You don't need to know how it works. However, I do love talking about it. So if you have a question, I would love to answer. But it's basically a way we can chemically determine what these particles are made out of. And so in this study, they looked at planktothrix from Great Lakes St. Mary's, and we can apparently look at it in the back if we want. But what they did was, just by looking at it, you really wouldn't be able to know what it is. But when you couple it with chemical information, each of these peaks is giving us all this information, and then we're able to exactly know that it is planktothrix. And this is one of the tools my lab uses so that we can collect aerosols and then know what we're looking at. And so right now, we're currently working on establishing the water and air connection through measurements and models. And this is where I partner with collaborators so that we can go out and do field work. And in this field work, we're collecting air samples, but we're also collecting water samples to bring back into the lab for that isolated laboratory analysis. And in this, we're getting our data and we're looking at it, and we're really trying to learn from it so we can improve the models. And then with improving these models, we're hoping to help exposure predictions, because at the end of the day, that's really what we want to work on. And so we're only taking measurements at one place at a time. We can't really be everywhere all at once. But how do we know really what's going on in the bloom then if we're not there? It's kind of the same way your weather app works. If you go on your weather app, you can look at any city all over the world and know what the weather is. But they don't have all the information for the whole atmosphere in that app. So how does it work? They have a few measurements, and then when you put together with a model, you're able to make this forecast. And that's the same way our measurements work, or our models work. So we go out, we do a handful of measurements on the lake, and then we couple it with an atmospheric model, and then we're able to know more broadly how is it affecting. And so here I'm showing one of those atmospheric models, and this is for all lake spray aerosols. So it's not just things from the harmful algal bloom. So you see low concentration is white, high concentration is purple. The high concentration is everything that's being aerosolized, not just anything from a harmful algal bloom. But this was the first thing that we worked with our collaborators to basically essentially connect what we know about particles in the area to what we know about the lake, so we can really predict what's getting up in the atmosphere. We also needed to look at kind of differences between blooms, and just between these two photos, you can see quite a big difference between the blooms from day to day. And then when you look at the filters, there's a huge difference. And so those edges is what the filter looks like before we start collecting. And on the 11th, you can see that there's much more particles, and the darker means more particles. So what we learned is that when there is a bloom, you are getting more particles coming out of the water. And we use this to then have an estimate of an inhaled dose. And I do need to specify this is an estimate and by no means perfect. But in this, you have your atmospheric concentration. And when you multiply it by your breathing rate, you can get an inhaled dose. And when you compare that with your peak bloom, you know that there is some difference. And in this difference is what we really need to understand. And I've heard Toledo is called the asthma alley. And so what we want to know is their connection with what's being measured, what's being aerosolized, and people's health, because that's really at the end of the day what we want to know. And that's where the Great Lake Aerosol Monitoring Research Community Health Study comes into play, or GLAMOR as I'm going to call it. But this study follows people who work and recreate in the lake to really understand, are these particles that are being aerosolized having an effect on human health? Because that's what we want to know. They follow around 200 participants for around 5 years to really understand and walk with these people to know what are the health effects of these particles. And I don't have enough time to thank all my collaborators, but I do want to thank my funding sources, because this research would not be able to be done without them. And thank you all for listening.
All right, again, we'll come back and Grace will answer some questions for you after we hear from Cal Buelo. So I'm going to call Cal up while I load his presentation. So Cal's coming to us from US EPA, and he's going to talk about some of the perhaps successes we're seeing with all the efforts that are going on across the landscape within the Maumee River Basin. Cal, again, I'm going to, for you, turn on, if you need the laser pointer. We've been doing this for 14 years, folks, now, and you're probably noticing now I have to wear glasses. That's how long we've been doing this exercise. Just forward and backward.
All right. Thank you, Chris. And thanks everyone for being here. I'm with the Great Lakes National Program Office based out of Chicago, and I work a lot on Lake Erie nutrients under the Great Lakes Water Quality Agreement with Canada. Today, I'm going to be talking about nutrient loads from the Maumee River, and specifically how we can correct or account for changes in flow from year to year using a method called flow normalization. These are results I'm presenting from a study that we're working on with a lot of people that are in this room. So we're hoping to have that submitted and go through peer review soon. All right, so to start, I want to reiterate a lot of what's been covered already today. Nate mentioned this and Rick as well. We see a lot of year-to-year variability in the loads that we got going from the Maumee River. And like Nate mentioned, a lot of that is due to, there we go. A lot of that is due to discharge variability, which again is very variable from year to year. I'll show the soluble reactive phosphorus loading from the Maumee River. This is just for spring going back to 2008. We can see that red line is the 40% reduction target relative to a 2008 baseline. And we can see, again, a lot of difference up and down, above the line, below the line. If we switch over to annual total phosphorus loads as another example to drive this home, this is a plot of the annual TP load against the annual average daily discharge. And we can see a very strong positive relationship there. And really about 75% of that variability is explained just by discharge in a given year. Switching back over to soluble reactive phosphorus again, we can look at these most recent years and we can see we've been pretty close to that target line overall. If we do the math and compare it to 2008 overall from 2020 to 2024, that's about a 34% decrease, which is great news. We want to be near or below that line. However, if we add the discharge line to this graph, we can see that discharge has also been down a lot over that same period. And if we add it up, that's about a 26% decline. So this suggests that a lot of what we're seeing is due to changes in discharge, which again isn't surprising. But just also want to highlight how we're expecting to see other changes in the landscape and the loads as well, but that big year-to-year variability makes it really hard to see. So the big question we are trying to answer with this study is how much of that change is due to discharge and how much is due to other things. And to do that, we used flow normalization. I'm going to get into how we answered that question in this study, but first want to dive a little deeper on the concentration discharge relationship, because it's really important to understanding how we can correct for changes in discharge and also how we can try to reduce loads overall. So again, discharge is a primary driver of loads. Nate had this on his slide as well, but its load is equal to concentration times discharge. In addition to that, we also often see very strong relationships between concentration and discharge. Here's an example from the Maumee for the spring for soluble reactive phosphorus, which I think Nate had DRP on his slides. These are the same things, just two different ways. Just wanted to clarify of referring to the same fraction of phosphorus. So again, we've got a really strong positive connection there. That explains why in the spring you can have really high loads when there's a lot of water flowing through and it has high concentrations. We can also think about how we want to reduce loads at the scale, especially of the entire Maumee River. It's really hard to have a control on discharge and decrease it. So really with a lot of the actions that we're taking, we're trying to reduce the concentrations, and that brings down the load to the lake. And then lastly, as I'm going to get into on the next slide, we can also use this concentration discharge relationship to understand changes in load separate from just whether it was a dry year and low discharge, low load, or a wet year with high loads, high discharges. So again, we're going to focus in on this CQ, Q is the symbol for discharge relationship. And the specific way we did that for this study is using a method called WRTDS, which is part of the EGRIT package, which is a really powerful statistical tool developed by USGS for looking at water quality trends. WRTDS stands for weighted regression on time, discharge, and season. And again, it's a method for flow normalization. We'll get into some of the methods a little bit in the next slide, but really the thing to keep in mind is that this was designed to eliminate the influence of year-to-year variation in stream flow on load. So you can kind of look at the non-discharge, non-stream flow changes. Before we jump into the method and results, I do want to just upfront give some important points to keep in mind about flow normalized loads and what they can and can't do. So it's really important to keep in mind that flow normalized loads do not correspond to the actual load in any given year. So whatever value you have for flow normalized load isn't going to tell you if the HAB was big or small in that year, for example. Also an important aspect of this method is that it uses a window of data in order to do its computations, and that window is both forward and backward looking. So every time we add new data to this analysis, it's going to change both your estimate of what the most recent flow normalized load was, but also can have an impact on prior years as well. So just to keep in mind that these things are not static, and so it's better to think of this on like a medium to long-term trend basis as opposed to like what a specific year and a specific number is. But then what this method does do is it gives us a statistical estimate of how these loads are changing without that influence of variability in discharge. And again, that can help us get some clues of what other things that are going on in the landscape. I'm going to go through the method in a little bit of detail, but try to keep it a little high level. And there's really three main steps to this WRTDS method. The first step is to estimate for each day, what do we expect that discharge concentration relationship to be? This plot shows two examples of this. So this is 2 different years, 2 different examples of what this curve might be. And this is maybe hard to understand because really you only have 1 discharge measurement and 1 concentration measurement on a given day, unless you're Heidelberg and you have up to 3, which is really rare and special and helpful for this. But yeah, this method uses all of the data that you've collected to try to estimate over a wide range of discharge. If we had seen a given discharge, what do we think the concentration would have been on that day? The second step is the flow normalization step, and this really takes that curve from step 1 and applies it to the distribution of discharge for each day. So what do I mean by distribution of discharge? This plot kind of shows it. This is for June 25th. This is the discharge that's been observed from 1976 to 2025. You can see that that biggest bar on the left indicates that in most years, you're seeing really low discharge on this day of around 50 cubic meters per second. But on rare occasions, we've got that one bar out on the far right. There's one year that was up near 800 cubic meters per second. So really, we're taking that curve from above, saying if we apply that to the distribution of discharge we expect to see on that day, that's how we compute our daily flow normalized or average or expected load. And the last step is the simple one, and that's just adding up all of those daily loads for whatever period you're interested in, whether that's the spring season or the entire water year. So that's a lot. And if you go any deeper than that, it gets a lot of math, a lot of equations really quick. So I just wanted to step back again. And really a way that we can think of flow normalized loads is how that relationship between concentration and discharge is changing. If flow normalized loads are decreasing, then that relationship is getting better. That's what we want to see. If flow normalized loads are increasing, that relationship is getting worse, which is not what we want to see. In terms of the data that we used for this study, you already heard all about it from Nate, so I'm not going to spend too much time. But we, again, focused on Maumee River with that Waterville site. And again, I'm going to talk about soluble reactive phosphorus and total phosphorus. All right, jumping right into the results. Before we get into what they're saying, I'm just going to step through all the parts of the figures that I'm showing. So we'll pop that up. First off, the blue line is the flow normalized load estimate for each year. Here we're showing water year soluble reactive phosphorus loads from 76 to 2024. You can see that most of that line is blue, but the most recent 10 years or so is dashed, and that's because those are the preliminary results. So as we add more data, those are the years that we expect to potentially change as if there's different relationships that we're seeing in that new data. So that's the dashed line. We got a 90% confidence interval, so that just gives us an idea of how certain the model is in those estimates in any given year. And then lastly, I've got the black points there are the actual loads, which I just want to include on these plots as a reminder that the actual loads the lake are responding to are not the same as flow normalized. But we can see it's a lot clearer to see these long-term trends when you're looking at the flow normalized curve, as opposed to all those black dots that are jumping up and down based on what's going on in that year. All right, so now moving on to what we actually see in the results. Again, sticking with soluble reactive phosphorus. This plot shows all of the Heidelberg data going back to the 70s results for it. And it really tells the story of long-term change in Lake Erie, starting with really high but declining flow normalized loads up until the mid-80s. Pretty low values from the mid-80s to the mid-90s, followed by an increase in the late 90s to early 2000s. That increase kind of leveled off and remained really high from 2005 to around 2015. And then since then, we've seen the start of a decline. So since around 2015 to 2024, we've seen decreasing soluble reactive phosphorus flow normalized loads. And if we do that 2008 to 2024 comparison with that baseline year, that adds up to about a 10% decline in SRP that we're seeing. So that's good news. Again, soluble reactive phosphorus is that most bioavailable form for the algae. They really like to take that up and grow. So that's great news. But again, that 10% is different than if we were just looking at the actual loads in recent years. We would say we were closer to 30 or 35%. So we're seeing signs that there's something besides just discharge going on. But really, in the last couple of years, a lot of the low loads have been due to low flows, low discharge. Switching over to total phosphorus, same plot, everything means the same. Again, can see some differences here. We started with high concentrations that then declined, a bit of a spike around 1990, followed by low values, and then jumping to, again, that around 2015-ish or so, we've seen an increasing trend in total phosphorus flow normalized loads. So again, this is indicating that relationship between concentration and discharge is not getting better, it's getting worse, which is not what we want to see, but in contrast with the soluble reactive phosphorus. So those are those two plots side by side, just so you can look at them next to each other. Again, the key kind of take-home point is over the last 10-ish years or so, we've seen a decline in SRP, but an increase in TP. I want to show one more type of result that we can get from this WRTDS method, and this is to get flow-specific estimated concentrations. So I'll pop up the SRP plot first. So here we've got three lines. The red line on top is high flows, so that's the 90th percentile. The green line in the middle is average flows, and then blue is low flows, the 10th percentile. And so this can give you an estimate of what the expected concentrations are through time, which can start to give us maybe some clues about what's happening in the watershed and further hypotheses to dig into. So kind of the key here one for SRP is we used to have really high low flow concentrations at the very beginning of the period in the 70s and 80s. Those dropped pretty quickly, and now we see the highest concentrations at the highest flows. That decline in flow normalized loads that we saw on the previous plot is really showing up in the high flow line there on top, the red, which is expected because a lot of the load is delivered at high flows. But we've also seen a decline in low discharge concentrations as well. Looking at total phosphorus, it's a little bit of a different story. It was a pretty steady decline across all high, average, and low flows, up to around 2015 or so again. And then since then, the increase that we are seeing in flow normalized loads is really happening at high flows and at average flows, while low flows have kind of continued to decline. All right, so just one more result I want to show. And this is really to highlight the impact that a single year can have on these flow normalized load estimates. Again, as a reminder, WRTDS looks at a wide window of years. So if a single year that you're adding has a different relationship, it can have a big impact. We have a really great example of this in the MOMI, and this is in 2019. There's a great study by several authors in this room that documented this, where 2019 was a really wet year, so much so that it prevented fertilizer from being applied in lots of areas in the watershed. And that in turn led to lower loads than you otherwise would have expected. It was still a wet year. There's still a high load over relative to other years, but less than you would have expected. And so for our analysis, we wanted to see what impact this one year had on the flow normalized load. And so to do that, we held out the 2019 concentration data and used all of the other concentrations. And so if we look first at total phosphorus for the spring for this analysis, we can see there wasn't really that big of an impact. We went from about a 16% increase and again, this is relative to 2008, a 16% increase if you include all years, and only a slightly larger 17% increase if you hold out 2019. That contrasts with soluble reactive phosphorus, where if you hold out those data, you get a smaller decline. So you go from a minus 10% change in flow normalized load to a minus 6%. So this really indicates that we had a much bigger impact on soluble reactive phosphorus in that year than total phosphorus. This is consistent with that prior study, but is just great to see that we can see it in a different way looking at flow normalized loads as well. And I think this is a great result to end on. One, just again, is that reminder that these numbers can and will change as more data get added. And so that's a good reason to keep looking at them. But then also just as a kind of encouraging note that if you do have a big year where there's a big change in the watershed, that will be reflected both in actual loads and in flow normalized loads. All right, so to wrap up, just I'm going to highlight those conclusions from this talk. Again, from 2008 to 2024, we saw an increase of flow normalized TP loads of about 16%, while SRP decreased about 10%. Again, that SRP trend is encouraging because that's the form that's most available to the algae. We saw that the flow normalized loads really mirror what we're seeing in recent years in the concentrations at high flows, which again is expected. And then one more reminder, I'll keep hammering on this, a single year of higher or lower than expected concentrations can have a big impact on these flow normalized loads as well. So important to keep tracking them and explore the causes. And then we also need to do some more work diving in to understand those differing trends that we're seeing between SRP and TP. I want to wrap up by thanking all my collaborators. Colleen's leading this manuscript that we're hoping to have through our internal review, and then submitted soon. I've got almost all the other co-authors in the room here except for Santina, so a lot of expertise, and I've really enjoyed working on this project with everyone. Thank you.
Al, if you stay here, and then our other speakers want to come up. So Rick and Grace, if you want to come up, and Nate. But I'm going to read some more questions. Again, there's some that came from the media that I'll try and address first, and we'll kind of tick through these. I have a mic on me, so if I come to you, you can speak into my collar, or I'll bring you a microphone. It could get a little creepy if you get that close. I did brush my teeth this morning, but I've had like 4 cups of coffee, so we'll see how that rolls. So I'm going to read a couple of these here. Again, they came in earlier, but now I think they're more relevant that we've heard all the speakers. So, and maybe not for the speakers here, but can we comment on the status of HABs in Lake St. Clair and the other 4 Great Lakes? And so there might be somebody in the audience here I'm going to look at our Canadian friend that is Mike McKay that's in here. So anybody on the up front, or Mike, raise your hand, get a hand raised. Somebody on the call wants to know what is the status of HABs in Lake St. Clair? Anybody? Mike's got it. I can run it over there. Mike McKay, University of Windsor.
Thanks, Chris. Yeah, we have a fairly consistent bloom in Lake St. Clair on the Canadian shoreline. So we have sort of a mini Maumee. The Thames River flows into the southeast corner of Lake St. Clair. Similar watershed, 80% row crop agriculture, lots of fertilizer flow. And then I think because the shipping channel of Lake St. Clair running through sort of creates two separate portions of the lake. And that constrains the nutrient flow into that southern portion. Every year, it's very consistent. So, whereas we see the variation in the Lake Erie bloom, we see a sort of a near shore bloom might go out a mile or so into the lake pretty consistently every year, usually late July, persisting until summer. Not so much on the U.S. Side, but there you've got Lingbia or Microcera, which is a bigger concern, which the Army Corps of Engineers has been working on.
Thanks, Mike. Just to comment on that, so the nutrients in the bloom that is in Lake St. Clair will ultimately enter the Detroit and actually get diluted. And so we can't forget about the fact that we're actually really lucky that the Detroit River has such a volume of water to dilute those nutrients in that bloom.
I comment a little on the other Great Lakes. Saginaw Bay has a bloom each year. It's not anywhere near as variable as the Lake Erie, and the biomass is smaller. It's usually not quite as, anyway, it's not as bad. Southern Green Bay does get blooms. They're quite variable between years. Sometimes they can be very intense. It's loosely related to Lake Winnebago, which the largest inland lake in Wisconsin. But there's not completely straightforward pattern. There's a lot to do with the oceanography in Southern Green Bay. And Lake Ontario, a couple of the adjacent tribs or estuaries have some local blooms. Lake Superior, the Apostle Islands have had a couple anomalous blooms. It's surprising Lake Superior being so cold, a cold water species, but that's only happened after very intense rainfall events. There's been 2 or 3 of those over the last 10 years and short-lived. Far Western Superior has some blooms in St. Louis River, and that's a local phenomenon. That's probably a few other scatterings around, but that's the key ones that are routine are Green Bay, Saginaw Bay, Lake St. Clair, and Lake Erie that we think of.
Thank you, Rick. The next one, really good question. So maybe some folks in the audience can help us with this too, but does this year's bloom suggest that all the combined mitigation efforts are adding up to meaningful progress, or does it instead underscore just how difficult Lake Erie's harmful algal blooms are to control? Stunned silence across the audience. I'll take a first cut. I mean, I love, Cal, your presentation, right? We know what part of that nutrients is tied to just discharge. You have more water moving through the system, you have more nutrients. But that doesn't control all, right? 75%, I think, was the number. And so we are seeing a 10% decline in that nutrient with all years included. Not if it's the 2019, it's the 6%. But that suggests we're doing something on the landscape and in the watershed that is making progress. And so I would say yes. And if you see it, again, that will change, but your data that starts to come down in that 2015 period, if you think about in Ohio specifically, this is when Senate Bill 150 came into play, which was if you applied fertilizer over more than 50 acres, you went through the 4R certification. And then, of course, in 2019, we know in Ohio, again, H2 Ohio, and then there was actually investments to help farmers get to places that we wanted them to get. And so I would say correlation isn't causation, but the timing of those impressive programs in Ohio, I think, can be tied back to some of that reduction. But I will also say, is we've done a lot of research and a lot of investment in how to slow that nutrients, and we're not at the 40% reduction. So I think for me, what I take home from this, and I'd love any other follow-up or comments in the audience, is I think what it illustrates is that we are chopping away at that nutrient influx, but we are definitely not done, and we have to continue our efforts and even arguably ramp up our efforts a little bit. And I'll pause there to see if anybody else wanted to weigh in or think about that comment or discuss that. Please.
We all know that global warming is very negatively impacting every life form on the planet. So, of course, this is driven by human population growth, which is exponential. We have here in the audience a lot of representatives and media people who can contribute for the knowledge of the audience. I think that Europe has a good idea. They have a value-added taxes. It's costing us a lot of money to improve the environment. So if we could tax, for instance, fertilizers and therefore improve our lakes and our environment, this is a message that I hope we can take out there. We are tracking the fertilizers, the blooms and all this, but let's get to the bottom. Let's get to the solution. Let's get practical. Let's see what we can do to make this a better place. Thank you.
Appreciate the question and the comment. I would say what I appreciate about the nutrient issue and the HABs issue we have is the solution is not just a science solution, right? And you're seeing a lot of that come out. You mentioned the word climate change. We know, based on the conversations here, that more rain can exacerbate this problem. Warmer temperatures can make that bloom start. So we need to know that science. But then we also need to know that when we go up in the watershed and identify where these nutrients are coming from, then becomes economic type questions. It becomes a social science kind of question where if we're asking, for example, maybe a producer or farmer to change the way they do things, we as scientists, we know our chemistry and our runoff, but we don't know as much about behavior and why they do what they do or why they can't do maybe what we're asking them to do. And so I'll highlight, we do have a little time that I want to put a slide up here at the end. We do have some projects. For example, there is research going on with NOAA GLEROS and the NOAA Great Lakes Environmental Research Lab to actually say what tools that exist out there. Is it giving us the right information? What do people want to know? Are these things that we're developing actually important? And so I'll highlight that a little bit. But I appreciate your comment. But this is not just our chemists and our biologists. This is our economists and social scientists being at the table. So it's really exciting to see all this disciplines interact. Tom, coming to you. Let me get your microphone, sir.
Yeah, not to confuse things here, but I had a story last Sunday, which you may or may not have seen, but we're talking about, the gist of what we're talking about is phosphorus, how much algae, how toxic it is. There's a group that George Bolerjan was with out at Lake Taihu in China, group of scientists, and George is one of the only U.S. scientists to go, and it also plays into some of the research that Grace has provided from University of Michigan, and Greg Dick's team there, says that what they've found is in algal blooms, it's not just toxins that humans should be worried about. There's kind of a toxic soup of pathogens, and about viruses, Rick, and everything else, but there are other nasty things in there that we shouldn't just be too limited or hyper-focused on how toxic a bloom is, that we should take a more holistic view of them. And I wondered what thoughts you guys might have about that idea that perhaps a more holistic view of the threat, the human health threat of a algal bloom should be studied.
Along those lines, one thing that I would say is a lot of these aren't one-trick ponies when it comes to toxins, right? They can make lots of different kinds of toxins, and depending on sort of the conditions and that sort of thing, they can express, different sort of concentrations of these different things. To the point of, other pathogens and bacteria and viruses and stuff that are co-occurring with these. Again, they're not the only things in the lake that can use that phosphorus, right? There are other things in the lake that phosphorus is beneficial to their growth, right? And basically anything that's alive. And so those conditions are great for growing all sorts of things that are bad for us. It's just, when they turn the light bright green, right, people notice. And so that's the thing that sort of, becomes the poster child of this. And so, yes, improving, the phosphorus conditions will help the algae blooms, but it's also going to help with these other things that are co-occurring with the algae blooms that can be detrimental to human health. So it is more than just the harmful algal bloom. It's also these other things that can be controlled by steps being taken to control the algae bloom, if that makes sense.
Well, and playing into some of our concerns about climate change, some of the thoughts are that the biology of the blooms themselves are changing through the season, and that the blooms that we've been seeing, the biology of blooms that we've been seeing, will likely be changing in future years even more.
Rick may be good to talk about sort of the different kinds of algae that exist and how they change throughout the season. Maybe Justin or somebody too. There's definitely people in this room that can get at that question, I think.
Well, the type of algae changes. The whole community does depend both on the nutrient level and the temperatures and how those work. And so there's different ones for cooler weather than warmer weather. As a simple thing, if I view the bloom from the point of view of, say, a drinking water plant manager, obviously Toledo is phenomenally concerned about toxin, but the reality is the biomass is a problem, just the stuff. And they have to get rid of the stuff, and they can't have organic stuff in going through it. So the fact that you have a bloom is inherently a problem if you're trying to treat water. And that organic stuff, they don't want any of it in there. And we don't necessarily know what's toxic. They just know we don't want it. So as a simple level, it does matter. I would say, boy, if you're talking, I would be cautious about, I think there's a correct statement to say that there's all kinds of things to worry about, but relating Lake Taihu to Lake Erie is a rather bold assumption as far as community. Lake Taihu is phenomenally in the middle of it's an enormous lake in eastern China. It's a phenomenally industrial area. Relatively, it's like the Western Basin surrounded by multiple cities. And so I think you're going to be dealing with a very different environment with that as well. So it's not to say there are multiple problems in any of them to worry about, but we should be cautious about how we treat, like I would say, Grand Lake St. Mary's and Lake Erie. They both have blooms. They actually have different kinds of blooms. The reason they have different kinds of blooms is because Grand Lake St. Mary's has radically different characteristics than Lake Erie. And so you end up with a different environmental problem. So it's one of the problems in ecological systems is they have a lot in common and they have a whole lot they don't have in common.
So if I might build, this is a great segue for the slide that I put up here. So many of you may not know, but there's a Great Lakes Center for Freshwaters and Human Health. The two logos to the right, it is co-funded by NIH and NSF. And under this program, you can see all the partners on the bottom. QR code will take you to the website. But this is hitting on where we just talked about, especially Tom, with your question and the question in the audience. How does environmental ability affect HABs, transport of toxins, and public health? And it's this idea of what known and unknown substances are produced by HABs. We often think about microcystins, but we now know there are other things in those blooms. What can we do more effectively to use regional data and other sources? And then the last one is, who is most needed this information? And so we're really trying to get these things about, environmental variability and how that impacts these blooms and what are other things in the blooms that exist. So I encourage you to go to this website and look at the work coming out of here. I have also highlighted Galero for the reason I mentioned earlier, is there is currently a grant going on where we're going to be conducting semi-structured stakeholder interviews about how they want their HABs information. And then after that, we're following it up with workshops, interviews, and surveys to really know the science and the data that we're getting, right? How are we getting this information into the hands of the right people? Is it people that live and play in the watershed? Is it health professionals? Is it the media? And so Tom and your colleagues, look out. We're going to be coming to you to ask, What do you wish you knew more about? Where is the data? Those sorts of things. So I'm so happy to have NOAA Glero in the audience, but there's a great project that's started up. Maybe one more question, and I'm going to bring it to you. This one comes considering, so Nate, this might be for you, considering that most of the P, both forms, was delivered during the April storm, and the SRP delivered was not higher than expected, but TP was. Does that imply SRP would have been below expected if there wasn't for that storm? You want me to read that to you again?
No, I think that I got it. No, not necessarily. SRP seems to be, the numbers seem to be about where we would expect. The increase in TP is really being driven by particulates this year. You know, that early April storm, high intensity, you know, carried a lot of sediment with it. Where that sediment came from, you know, we don't necessarily know. But this year, you know, the DRP sort of looked like what we would expect, especially based on sort of the last, you know, 4 or 5 years of what we've seen. But we got way more particulates this year than I think we expected.
Great. I'm going to ask one other question of this group. It's a very high-level question. As we do that, I'm going to get help from the IT. I believe we have a recording from Congressman Dave Joyce's office on the computer. Is that true, Zach? Okay, well, we'll work on that. If not, we will make sure that that gets put up on the website. Congressman Dave Joyce wanted to be here in session, so send some remarks about this effort. So if we can't get it to play audio here, it'll be on the website, and we'll push people there. So the question that's up, and we're supposed to close down at 1. We have a history of going over a little bit, so that's okay. But the question here that came from one of our press folks, our media folks, is what is the biggest misconception the public has about harmful algal blooms? And maybe what part of the story isn't receiving enough attention? So either one. What is a misconception, or what is something that should get a little bit more elevated attention? And I'm happy to look to the audience if our speakers are stumped. We got one back there with Lord Johnson. Oh, more Michigan people in the room. It's fantastic. Please.
I think the biggest misconception is that how harmful algal blooms are everywhere in Lake Erie all of the time, and you can't get away from them. And I think, so I know Rick would say this, but I'll highlight that, you know, when the bloom forecast maps come out and they have geographic reference, like look to those. Not everywhere in the Western Basin is untouchable, even during peak bloom times.
I'm coming to Andrew to answer too. Andrew Frubley.
I think one of the areas that the public really needs to know about is what Grace was talking about. Because when we think, in Grace, you did a fantastic job. We think about drinking maybe 1 liter or 2 liters of water a day, but I think we breathe something like 10 or 11,000 liters of air. So I mean, and I would love to know what you think, that's something that the public is not thinking about.
Yeah, so just because you know it's in the water, you don't know it's in the air. I think that was probably the biggest thing that stood out to me. When I started learning about harmful algal blooms, some things aerosolize more readily than others. Others literally just want to chill in the water and aren't even seen in the aerosol form. So I think that's a huge thing, and that's exactly like what my lab is looking at, is trying to understand why these things are being aerosolized and like how can we learn about them and like what they are like aerosolizing about.
The question was, any maybe thoughts from Grace or Andrew about safety precautions people should be taking? Yeah, I would argue.
Yeah.
So I think it's too soon.
Pioneers in this, we don't know enough yet. It's not ready to sound an alarm, but.
And I think that's the.
Would it be advisable for people to consider not boating in scums, even if they're not swimming in it? Maybe scums aren't the best to go through in a boat. Does that sound like a reasonable estimation from what your data are showing?
Microphone back to Grace. And I can weigh in on that too. And I know, so there is a recreational impairment designation for the open waters of Lake Erie. So the US EPA lifted that up. There's a publication out there on that. So we know, you know, when the lake is where it's at, you know, hey, if you're recreating, know that there is a risk here. I would argue that it's easier to post a risk sign at a beach than it is 18,000 buoys sitting out in the middle of the lake. But perhaps the misconception is we need to be talking about aerosolization exposure. But Andrew, to come back to you, not like crazy alarm bells, right? The science is still in its infancy. When Grace shows, a low bloom is this amount, here's how much is in the air, here's how much you breathe in, this is what you're exposed to, versus a bloom season one, we don't know if that bloom season one still has pushed just over the edge. And I know that Dave Kennedy's in the room and over in the corner from University of Toledo. Definitely a lot of the work you've done in the human health space says, as far as the general population, the exposure may not be to the point where alarm bells are going, but there are segments and sectors of the population. For example, Grace pointed out the asthma belt, people that have, non-alcoholic fatty liver disease or irritable bowel syndrome. So I think there are things that we know enough about to say, hey, there is something here, but we don't need to blow this thing out of proportion. So coming to Dave Kennedy and then coming in the back.
Yeah, I think that's perfect. And follow up on Laura's kind of like, the bloom isn't everywhere. One of the things that we're trying to understand with the Great Lakes Center for Freshwater and Human Health is we know that if 100 people have a headache and they all take Tylenol, it works great for 85 people and then 15, don't respond. So we're trying to understand and tease out in a long-term way who responds and who doesn't respond. We know some people are more resilient. We're trying to understand what confers that resilience that, to aerosolize toxins, and then also what makes people more susceptible. And that's going to be super important. And I think also one of those unanswered questions are, we know what happens if you are exposed to a metric ton of microcystin. What we don't know is what happens when you're exposed to a very low level over a very long period of time. And so that's just, like everything, it's just going to take time to figure that out. But that's what we're doing.
Yeah, I'll just add something. When I'm not doing Lake Erie, I happen to be dealing with red tide in Florida, which does have a toxin that is known to aerosolize. And for most people, there's no evidence that it causes any problem except the very immediate one. But if you have asthma or emphysema, it's a significant problem. And you can wear an N95 mask, actually. It does work. The lifeguards figured that out long before COVID. And of course, asthma meds. But so an important thing here is it's figuring out what is the factor and who's at risk. And it may be that it's only certain people, but we need to know that. That's a key part of the whole question is who's at risk and in what way. And that definitely matters.
From Austin Cerno,
Yep.
Captor's office.
So we talked a lot about the aerosolizations, and thank you for sharing that. Obviously, also in Lake Erie, there's a large fish population, and that's a lot of our tourism and economic. With the algal blooms, fish ingesting it or dying from it, but also we eat that. Is there any study or data that the fish that we're eating and the chemicals that we're also ingesting?
I can give you a real high level, Austin, on that. So the DNR collects fish. The DNR then works with Ohio EPA and the Department of Health to fillet those fish and look at the edible portions of those fish. There are fish sometimes that you will find that will have some concentration of those toxins, HAB toxins in the fillet, but they are well below where the health recommendations are. So when you look at fish consumption advisories in not just Lake Erie, but some other lakes, it's still, most of them are primarily driven by mercury. Not all, but most. So the consumption advisory in Erie is still based on mercury. And so I would tell you, in talking with my agency colleagues, and if somebody in here, one of those agencies wants to raise their hand, is if I brought my kids up here and caught a fish, I would be eating that fish. And if I lived in a community that drew its water from Lake Erie, I would be drinking that water from Lake Erie, right? This is something we need to work on. But because of that issue, the drinking water advisory in Toledo, you don't want to waste a good catastrophe. And I can tell you that we have scrambled in the exposure, the drinking water place that I feel real safe in the Lake Erie watershed. The beaches are another thing, right? If there's a scum there, as Rick said, keep your dog out, keep things out. We will keep working on the aerosolized question, but have confidence in where we're in the direction we're moving. We're doing good things. We're well over, so I just want to pause and thank all of our speakers today, if we could. Also, this room is full, and I know the webinar is full too. You guys are taking time out of your day. I know you're on an island, so I'm not that taking time out of your day. And again, this is why I like going to work. These are the people I love working with, the agencies, the academics, the elected folks. This is great. And I'm really appreciative of this. I'm appreciative of the press that come out and help us elevate the message and get it out. So a round of applause to everybody that's in the room and online. Okay, I'm seeing from the audio. What do we got? Let's do the video. Let's close out with words from Congressman Dave Joyce then. I wish I wasn't so fumbly on the webinar. We'll keep this rolling. For those of you online, if you dropped off already, I'm sorry, but you're going to hear Congressman Dave Joyce. For those of you that are on the island, we will feed you next. But if you have to get off the island, we'll get you off the island. Again, just want to say thank you. A lot of people came up saying thanks to Ohio Sea Grant and Stone Lab, and we appreciate that. We appreciate hosting, but it is everybody in this room that does this work. And
Hello, everyone. Congressman Dave Joyce here. Welcome to NOAA's 17th Annual Harmful Algal Bloom Forecast, hosted by the Ohio Sea Grant at OSU's Stone Laboratory Island campus. Like many of you, I have fond memories of spending time on Lake Erie with family and friends. The cultural impact of these national treasures cannot be overstated, and we must protect them for future generations. The Great Lakes are also an economic powerhouse. They support 1.5 million jobs and generate $60 billion in wages annually, providing an entire region with opportunities we can't take for granted. And they're critical to our environment and national health. The Great Lakes are home to more than 3,500 plant and animal species and provide drinking water to over 40 million people. Protecting them from contamination isn't optional, it's essential. During my time in Congress, I've fought consistently to do exactly that. I've been lucky to have great partners in this work like Ohio State and the Sea Grant program. As co-chair of the Great Lakes Task Force, I've introduced legislation to reauthorize programs critical to this mission. The GLRI Reauthorization Act funds the most comprehensive Great Lakes conservation effort in history, helping fight invasive species, restore coastline, and prevent contamination. The Beach Act protects our recreational waters and helps identify contamination at the source. I was proud to see both bills pass the House earlier this year, and I'm hopeful they'll advance soon in the Senate. I've also introduced the Harmful Algal Bloom and Hypoxia Research and Control Amendments Act, part of the reason you're all here today. This bill improves the forecasting and prevention of harmful algal blooms, helping make Lake Erie safer and healthier for everyone who depends on it. The work you do at this forecast matters. It turns science into action and action into cleaner water. I'm grateful for your continued partnership, and I look forward to what we'll accomplish together. Thank you.
I said that was going to be the last remarks, but what a great way to close, right? We need investments to prop these things up. GLRI has been amazing for the Governor H2 Ohio, Habarka. So these are all great things. And so appreciate you being here. Appreciate you all being online. And we'll see you for the 15th one in about, it's always the Thursday before the 4th of July. So mark it on your calendars. Thursday before the 4th of July. Thanks, everybody. And we'll close down the meeting.